If the energy field density remains the same during cosmic inflation, how does that also agree with the conservation of energy principle, since the energy would be increasing exponentially with the space increasing and density remaining steady? The answer, shocking though it may be to hear, is that energy isn't always conserved, and cosmic inflation actually violates energy conservation in a particularly extreme way. Here's what's going on. It turns out that if you want to know what's conserved in the universe, you need something specific that underlies the rules that govern your system, a symmetry. There are profound connections between symmetries and conserved quantities, and they were first revealed more than 100 years ago by one of the unsung heroes of physics and mathematics, Noether. She wrote two important proofs, published in 1915, whose content showed for the very first time that if you had the following three criteria in place: a physical system where the forces at play are conservative, the force of one object on another leads to an equal and opposite force acting back on the first object, whose action has a differentiable symmetry, then each and every independent differentiable symmetry that it possesses will also lead to an associated conservation law. If there's a conservation law, then there's a conserved quantity. That is the core of the deep connection between conserved quantities, like energy, and conservation laws, like the conservation laws, and symmetries in general. In other words, these proofs, now known as Noether's theorem, tell us that every time you have a physical symmetry within your physical system, then there's something physical associated with your system that will be conserved. There are many important examples we can look to that illustrate this powerful connection. If your system is symmetric under rotations, then that system's angular momentum will be conserved. If your system is invariant under spatial translations, that is, you can move to any location and still recover the same system, then that system's linear momentum will be conserved. If your system is invariant under boosts, also known as velocity transformations, then it leads to the conservation of force momentum, the center of mass theorem. And if your system is invariant under time translations, that is, your system is identical to how it was in the past or will be in the future, then it leads to that system's energy being conserved. That last item is of particular relevance here. If your system doesn't change with time, if its laws and properties are indistinguishable whether you examine it earlier, later, or right now, then energy must be conserved within it. But the converse is also true. If the universe evolves with time, and an example of evolution is the distance between 2 points within that universe changing with time, then there isn't anything mandating that energy be conserved at all. This might puzzle and confuse you. After all, energy conservation isn't something that we realized was a property of the universe because of Noether's theorem. It was something that was uncovered empirically by quantifying and measuring the total amount of energy initially present in a system that's added to or removed from that system, and then that exists in that system in its final state. If the initial energy plus or minus the energy that's added or removed to the system is equal to the final amount of energy in the system, then energy is indeed confirmed. If not, then energy conservation is violated. For laboratory systems here on Earth, energy is indeed always conserved in exactly this fashion. When you collide two particles together, no matter what it is that goes into or comes out of your experiment, the sum total of all the different initial energies and the initial final energies will always match. When you release a particle in the gravitational field of the Earth, whether you shoot it up, throw it horizontally, or let it fall, the total sum of the particle-Earth system initially and at the end will always be equal. In fact, under all four fundamental interactions, gravitational, electromagnetic, or even the weak and strong nuclear forces, any physical system examined here on Earth has always been observed to conserve energy. But if you leave our cosmic backyard behind, things are no longer so simple. If you were to shine a light outward into the broader universe from planet Earth, it would start to appear as though energy was indeed still conserved. As the photon, the quantum of light, that you created rises up through Earth's atmosphere and into space, it loses energy, causing its wavelength to get longer. This isn't a violation of energy conservation, however. Energy is conserved because the photon's energy loss is exactly balanced by the change in gravitational energy as it moves farther away from the center of the Earth. This same process continues as the photon leaves the solar system. It loses energy and lengthens in wavelength as it moves farther and farther away from the sun and the other planet, trading a gain in gravitational potential energy climbing out of the gravitational potential well, for a loss in the photon's kinetic energy. As the photon escapes from the gravitational pull of the Milky Way, the same thing happens. Energy loss in the photon's kinetic energy is balanced by the gravitational potential energy it gains by leaving the gravity field of the object it originated from. This continues all the way up to its escape from the local group, which is the last time that total energy is conserved. Once the photon enters true intergalactic space, the story changes dramatically, however. As it travels through the universe, it now loses energy, with no other form of energy experiencing a corresponding gain in energy. What's happening here? Once a photon, or any form of energy for that matter, leaves the local group of galaxies, it's no longer part of a gravitationally bound structure. Instead, it's just traveling through space, through the expanding space of the broader cosmos. After all, we've known for right around 100 years that the universe is expanding, as it was both predicted theoretically and measured observationally back in the 1920s. When the universe expands, the distance between any 2 points gets larger over time, including the 2 points that define the size of a wavelength for any individual photon, or quantum of light. In other words, as the universe expands and a photon travels through it, its wavelength stretches to longer and longer wavelengths, which in turn takes it to lower and lower energies. A photon's energy is defined by its wavelength. This time, the energy doesn't go anywhere. The final energy is simply different from the initial energy because energy is not conserved within the expanding universe. After all, without time translation symmetry, there is no corresponding conserved quantity of energy, and a universe that expands, or contracts for that matter, is fundamentally different, particularly in terms of the distance separating any 2 points from one moment to the next. For radiation traveling through an expanding universe, energy isn't conserved, it's lost. But radiation isn't the only type of energy allowed to be present within our universe. There's also matter, both normal and dark. Neutrinos, which behave like radiation when they have lots of kinetic energy and behave like matter when they have very little. Topological defects, such as cosmic strings and domain walls, which may be theoretical only. And energy inherent to the fabric of space itself. That last form of energy shows up in many different fashions. A cosmological constant, known as lambda in Einstein's general relativity, behaves as a form of energy inherent to space. The vacuum energy of quantum field theory, also known as the zero-point energy of space, behaves as energy inherent to space. Dark energy, which drives today's modern accelerated expansion of the universe, is a form of energy inherent to space. And early on in cosmic history, during a period of cosmic inflation that preceded and set up the hot Big Bang, the energy inherent to space was enormous and drove the universe to expand at an exponential rate, doubling in size in all 3 dimensions with each tiny fraction of a second that elapses, all while its energy density remains constant. That's the key feature to a universe that has energy inherent to space. As it expands, new space gets created, but the energy density remains constant. Same density but more volume means more total energy overall. Whereas a radiation-filled universe, that is, a universe filled with photons, loses energy as it expands. A universe filled with energy inherent to space, that is, the inflating universe, gains energy as it expands. This isn't a bug. This is something that's mandatory in our expanding universe. Because there's no time translation symmetry. Because the universe at any moment is different from the universe at either the previous or the subsequent moment, energy is not conserved at all. It's tempting to state that depending on the type or species of energy present within the universe, the total energy is something that can either decrease, like for radiation, or increase, like for inflationary energy. But a more truthful statement would be that energy is not even well defined in a universe without time translation symmetry. In an expanding universe, there is no consistent definition of energy at all. Why is it impossible to define energy in a universe without time translation symmetry, such as in an expanding universe? Consider a comparison with electromagnetism. When things with electric charges move apart, for example, it's because either some conservative force, like the electric force, is pushing them apart from one another, or some external force is being applied over a distance, performing work on those particles in order to move them. Since work is just another form of energy, And because the equal and opposite forces that act on these charges conserve the total kinetic plus electric potential energy, it's easy to see that energy conservation still holds. But for gravitation, things, including things with mass and/or energy, can move apart because there's a conservative force, like a periodic comet departing from the sun. Or they can move apart because the fabric of space itself is actually expanding. In the first case, of a comet orbiting the sun, the changes in distance and speed of the comet-sun system result in energy being conserved, as the total initial energy and the total final energy will be equal. But in the second case, of a universe that's expanding, there isn't a good way to define what the total energy of the system is, because there's no objective, unchanging reference frame to define it with respect to. Because we can observe and measure that the universe is expanding, that means that relative positions and distances change over time. Consequently, so do any energy-dependent quantities that depend on the amount, distance, or space that objects occupy, including quantities such as wavelength, gravitational potential energy, and the volume of space, with a positive constant energy density during inflation, enclosed within the observable universe. People often ask whether it costs energy to expand the universe, or whether we would gain energy if the universe stopped expanding and began contracting instead. But this assumes that separating objects with energy is a thing that costs energy in the first place. That's only true in a non-expanding, non-contracting universe. The expansion of space is free in the sense that it doesn't cost any energy at all. It occurs over time for free, as an inevitable consequence of the expanding universe. It's kind of funny, when you think about it, that this is one very, very important case where the old saying that there's no such thing as a free lunch doesn't apply. When the universe expands at an exponential rate, both during inflation at early times and during dark energy domination at late times, there is something that you do get for free: extra amounts of space. Empty space under these conditions doesn't cost a thing. As it gets created, it comes along with the same energy density that the space that created it also had. Does that mean we get free energy from inflating or any exponentially expanding space? I wouldn't look at it that way. Global energy is not something that's well defined for an expanding universe. In fact, if you don't have a time translation symmetry to your universe, including for your space-time under Einstein's relativity, that ensures that energy is not conserved. It's tempting to attempt to redefine energy in such a way to include the work done by a patch of space on its surroundings, both in positive, for example, from radiation, and negative, for example, from dark energy forms. But the only thing you gain from that is your own personal satisfaction from having concocted a definition that allows this new thing to still be conserved in the expanding universe. There is nothing useful, extractable, or applicable about it, however. It doesn't behave like energy in the conventional sense. It's just a redefinition driven by our own biased sense of aesthetics. Cosmic inflation does indeed violate energy conservation, but not because there's anything special about dark energy or a space-time that's exponentially expanding with a constant energy density. As long as your space-time lacks a time translation symmetry, energy conservation is violated. Moreover, an energy definition is not rigorously possible under such conditions. Symmetries play a key role in physics, but there are many symmetries our universe simply doesn't display. As long as your universe expands, contracts, or changes with time, energy won't be conserved there either.